Today is our fourth lecture, and the previous one was about the basics of finite difference. I think maybe, yeah, that's okay. So the previous lecture was about the basics of finite difference schemes, actually from theoretical point of view. So I tried to explain you some main theoretical concepts behind the numerical solution of ordinary differential equations. So we discussed the convergence, consistency, and stability, and relationship between all these concepts on the example of just one linear ordinary differential equation. This time I'd like to remind you the main results, the main outcomes of previous lecture, and discuss some practical features. So the thing is that here there is strong coupling between theory and practice, and I'd like to show you that all the things that we have discussed previously. So we discussed on previous lecture. You can see all this feature in practice. So that's the main idea of this lecture. But first of all, I'd like to remind you the main results previously. So we discussed that, for example, we have some differential problem like ordinary differential equation, or later we will discuss partial differential equations. And this is the formal notation for that. Lu equals to F or is equal to F, where L is abbreviation for some differential operator. For example, Lu means U prime plus AU. So it means the action of operator L on function U. And suppose LHUH is the abbreviation notation for our finite difference scheme. So here LH is some finite difference approximation of our operator L, and UH is a known grid function, and we would like to find this grid function. For example, on the example of just explicit Euler scheme, LHUH means this one. So this forward approximation for derivative and the term AUN. And we discussed that if we would know the exact solution, so in this case we can estimate the quality of our numerical scheme. So if we would know the exact solution, we can compare the numerical solution and the exact solution and understand the main properties of our numerical scheme. We can understand the accuracy order. So that's the most important parameter characteristics of our numerical method. But the problem is that usually we do not know the exact solution. And how can we check that the numerical method works well before simulation? Or how can we estimate the properties of simulated result after simulation? So for that we need the understanding about the consistency and the stability of our numerical method. So the general flow path is as follows. So consider our numerical scheme and then put the exact solution. So U in square brackets is the exact solution defined in a set of nodes corresponding to our computational grid. So we put this exact solution to our numerical scheme, and although this is the exact solution of our initial problem, not the finite difference problem, we will get some truncation error, delta F. And so the numerical scheme is good, it is convergent. If delta F goes to 0 as H goes to 0, it means the consistency. It means that our finite difference approximation is consistent with the initial difference problem. And the second very important feature is that delta F makes little difference to UH. So it means that we can consider this delta F as a perturbation to our numerical scheme. And our numerical solution should be stable. It should not change drastically, significantly, when we give this small limited perturbation. If both conditions are valid, then the numerical scheme is convergent, and this is the essence of Lax Equivalence Theorem. And this was the example for Euler scheme. I showed to you how to check the consistency of the numerical scheme. So in fact, this is the example of analysis for consistency. And the main result of the previous lecture was the Lax Equivalence Theorem. So I provided more details about the proof of this theorem. So one more time, we assume that the numerical scheme is consistent with the problem and with an accuracy of h to k and is stable. So we assume that numerical scheme is consistent and stable. Then the solution of the finite difference problem converges to the exact solution, and the following estimation is valid, where a constant C2 comes from the definition of consistency and C3 from the definition of stability. So we formulated the definition for consistency. It means that this truncation error delta f is less than C2 h to k, and the definition of stability. It means that the norm of difference between the disturbed solution and non-disturbed solution of our finite difference scheme, the difference is small, and the constant C3 goes from the definition of stability. One more time, so today it's important to specify that what is UH. So UH is some linear normed space of functions. So one more time, we need to be able to compare between each other different functions, different grid functions. So not just in one point, on average. So we should have some tool to compare, to measure these functions. So this tool is a norm. That is why all our grid functions are submerged into some linear normed space of functions. And FH is linear normed space for right-hand side vectors. And how can we prove this theorem? So the main idea is that I have already explained it. So in the definition of consistency, this delta f can be considered as perturbation. So we can regard the truncation error as perturbation of the finite difference problem. And then we can combine the definition of consistency with the definition of stability. According to the definition of stability, the norm of difference between function after perturbation and before that should be less than some constant multiplied by the norm of this perturbation. And we can apply this definition to definition of consistency. And in this case, epsilon is delta, and ZH is the exact solution. And then we can put this the epsilon and Z to definition of stability and get the norm of difference between the exact solution and numerical one. It's less than C3 to norm of truncation error, but the norm of truncation error in turn is less than C2 h to k. That is why, so the theorem is proved very easy if we take into account the definitions, if we know the definitions, the formal definitions of stability and consistency. And we also discussed that, so what does it mean that UH is a, what is it? Linear normed space of functions. Okay, so this is the theory, but now we should specify how can we use this formal definition in practice. For that, first of all, we should define, so what does it mean, the norm, and which space functions do we mean? So commonly used function norms for assessing the accuracy of numerical methods are the following. So now I'd like to explain you how can we estimate, measure the accuracy of numerical methods on practice. So for example, we have our numerical method, we can implement it in code, we can do some simulations, we can get some result, and we want to estimate the accuracy of our result. How can we do that? First of all, we should choose the norm with which we will work. So the most commonly used norms are here. So this is one norm. One norm is the following. So h multiplied by the sum of absolute values of our function. So suppose we have a segment, for example, from 0 to 1, and we have a grid, so a set of nodes on this segment, and we know the value of our grid function for each grid point. Then we can compute the summation of absolute values of these values of our grid function, and also multiple it by h. So this h is important because actually this norm comes from integral norm. So actually this is an analog for just integral of function f from the beginning to end of our segment. So it's a finite difference analog for integral. So or we can use two norm or Euclidean norm. So we can substitute the summation of absolute value of our function to squares, and after that take a square root. The thing is that there's a theoretical statement that in actually all these norms are equivalent. So it means that if you will measure the norms using one norm or two norm, for sure you will get different results. I mean the different values for this norm. But the behavior of this norm with the variation of h should be just the same. So that's not too important which one you will take for your analysis. And infinity norm or maximum norm is as follows. You analyze the absolute values of your components of your grid function, so for each node, and just take the maximal value. And this is also a norm. It's possible to prove that, I mentioned last time that norm is a function that should satisfy to a number of requirements, and it's possible to show formally that so all these objects 1, 2, and infinity norm are really norm. So they indeed satisfy the necessary conditions for the function to be a norm. So all these norms are really used today for estimations of properties of the numerical schemes. Last time so this is a summary of numerical schemes that we have already discussed. So, and I'd like to show you how if we will implement in code these schemes, what we will see. So we considered the initial value problem for the ordinary differential equation, this one. And we discussed, and now we are going to implement and examine the properties of the following numerical scheme. So first of all is the simplest possible Euler numerical scheme, explicit Euler scheme. And previous lecture I showed to you the curves, the numerical solution of this ordinary differential equation for A and B that we have chosen to 3 or 2 or something like that. And I showed to you the variation of this solution when we change the the grid size. So the first scheme is the explicit Euler scheme, and we also proved that the accuracy of the scheme is big O of h. So it's the first order scheme. Then we discussed that okay, maybe the first order scheme is not enough. We would like to have the second order scheme. And we discussed the general approach. How can we do that using a method of undetermined coefficients? How can we build more accurate finite difference representation for this first derivative? And so the second candidate for that, if you want to have more accurate result, is central difference scheme. So this one, now we substitute the d over dx using this central difference scheme. And we discussed that there is a problem. The problem is that we do not know u1. So to implement this scheme, we know u0, it corresponds to initial value, but we do not know u1. And I will show you today that it's very important actually. And we proved theoretically, so it's just this summary of our theoretical results from previous lecture. So I understand that maybe it was not very clear maybe on previous lecture, but this lecture will help you to understand the previous one. So we proved that if we will take u1 equals to u2, then the scheme should be convergent, and the accuracy of the scheme should be big O of h. But at the same time, if we will choose u1 more accurately, so you can see that this follows, so it can be considered as just one step of explicit Euler scheme, right? You can see here. So it's also the general approach. So if you have a big stencil and you do not have enough points to start your computation, you can do a number of first steps using low-order schemes, just to get the necessary number of initial points, and after that you can switch to more accurate numerical method. So we proved also theoretically that if you will choose u1 like this one, the accuracy of the numerical method will be a big O of h squared. And this is how the un plus 1 can be expressed via un and un minus 1. And finally, we also discussed that, so it was an example that the consistency is not enough. So I provided you with this example. So this is the first order scheme, big O of h. So it's a sort of mix, a blend between the first order scheme and second order scheme. And finally, the final numerical approximation for the d over dx will be the first one. So it's the first order scheme, but at the same time it's unstable. So it means that if you will run simulation and we will check it, you will see that you will not be able to get any relevant result. So very fast, after just several times, after several steps, the solution will blow up, and so you have nothing in common with the exact one. And here how can we express the UN+1 for convenient implementation of this numerical scheme? So 1, 2, 3, and here two different options. So we are going to check all this stuff. After simulations, after computations, we need to estimate the accuracy of numerical method. So two options are possible. How can the order of accuracy of method be estimated in practice if the exact solution is known? So suppose that we know the exact solution, like in the case of our ordinary differential equation. How can we estimate in practice the accuracy of our method? Actually, we have already done it, but just in one point on previous lecture. But now we want to do it for the whole segment. From the definition of the convergence, we have that the difference between exact solution and numerical one in some norm. I have explained to you so which norms are commonly used in practice. It's an order of magnitude CHK, where C is a constant and H is is a step, is some small parameter, and K is the accuracy order of our numerical method. For sure, it's not equal to. It's not equals to, but so there are some other terms, but they are considered to be small. Take a natural logarithm of both sides yields. So now we take the natural logarithm from the left side and to the right side. So the logarithm of the product is the summation of logarithms, logarithm of C plus K logarithm H. So what does it mean? It means that it's a straight line. So in the coordinates logarithm of error and logarithm of H, so this is a straight line, right? With the slope equals to K. If we compute the error norm for several grid resolutions, so we can take H1, H2, H3, we can take more detailed computational grid, for example, H, then H over 2, H over 4, and so on and so forth. And then we compute logarithm of H and logarithm of error in some norm, and put all these points. We should have the result that they should approximately line on the straight line with slope equals to K. So for sure, that's not exactly, because we have some additional terms here and so on. But nevertheless, so when you do simulations for example, 3 or 4 or 5 computational grids, you will get these 5 points in this space: logarithm H, logarithm error. It should be just a straight line, and you can measure for example, using some regression analysis. So it depends on the accuracy you would like to have for this K. We can estimate the accuracy order of the numerical method. So usually you do not need to know very exactly. So you should have just some general understanding. So either your numerical method is the first order or the second order or some fractional order. So for sure, in practice, you will get some 0.9 or 1.1 and so on. So this is the option. What should we do if we know the exact solution? We know this guy, U in square brackets. But what if not? And what if not? We can use the approach called Richardson extrapolation. So Richardson is one of the founding fathers of CFD. Next time, when we will discuss numerical methods for just linear direction equation, I'm going to explain to you his contribution to CFD. So he's considered to be the first who implemented the numerical method for partial differential equation and computed some physical problem. It was at the beginning of the 20th century. So actually Richardson extrapolation is an approach how to increase the accuracy of your numerical method during integration, but it can be also used for estimation of the accuracy of your numerical method. So suppose that we move from one point to another point and the step is H. Then we can say that approximately UH is the approximate solution, so U is the exact solution, and we do not know the exact solution. But we suppose that numerical method has the accuracy order k. Then we can say that UH is U plus CHK plus big O of HK plus 1. Then we can compute the same problem using the H/2 computational mesh. So then the exact solution should be the same, right? And numerical scheme is the same. It means that we can just substitute H here, so it's CH/2K. And the rest terms, so they will change somehow, but we believe they were small. And then we can compute it for the computational grid H/4 and have this formula. After that, let's take the summation. These two equations and then these two equations. So for the transition from H to H/2, we have this. So absolute value of difference. So it's a absolute value of difference of our numerical solutions. Once again, here just in one point. Here is just the idea. Then U and U. So we don't have them. They destroy, and we have only CHK 1 minus 1 over 2 to K. And we can do the same thing for H/4 and H/2 once again. And then we can take the ratio between this one and this one. And again, we don't have C anymore, HK, and this guy, and have only 2 to K. And the K is logarithm with base 2 of this function. So it means that if we have 3 computations on 3 different meshes, we can try to estimate, at least to get some knowledge, some understanding of the accuracy of the numerical method. And indeed, in practice, so when you do some simulations and, for example, write a paper, and the reviewer can ask to provide any relevant estimations of the accuracy of the numerical method. So usually we know from theoretical point of view that the accuracy of the numerical method should be like 1 or 2 or 3 and so on. But always, so usually it's interesting to know what the accuracy order is implemented in reality. Because in reality, usually, especially in the problems with strong, gradients of parameters or even discontinuities, usually the practical accuracy of the numerical method is lower or equal to theoretical one. It's the just common thing. Okay, so these are the preliminary theoretical results, and now we can move to practical part. You can write your own code using any programming language, but I prefer C with some features of C++, because actually that nowadays there are Java, Python, many other languages, but as for scientific computations, surprisingly, but still, for example, Fortran is very popular, C++ is very popular, because if you need to run your simulations on supercomputers, so just standard common languages that they're still used. And also, the second problem is that a huge number of solvers and codes have already been implemented, and always you're not able to rewrite them using modern programming languages. And for example, for different modern computational architectures and so on, that's a big problem. That is why still we have a large number of codes written in C, Fortran, and actually they still alive. So I use Visual Studio Media, Visual Studio System. Actually, I can okay. I can show you how to start with. Okay, so we should just file a new project, and then we create the new project. We do not need anything inside it. Yeah, so usually in C we have source code files and header files. Let's create the main. C is just file with our code. And usually all constants, so in our problem we have a number of constants such as the A and B will be the right and left ends of our segment. We have the parameters of our numerical method such as this. Oh, I can switch, right? So now we want to implement all these numerical methods for the solution of this problem. So we have constants, this one, 0, 1, we have A, we have B. Usually they are placed here in hero file. H. So a very important thing, maybe one of the most important things, that your code should have many comments, because after a week or months or several months, even you will not be able to remember what did you implement. Not saying about other people who will try to do when they will try to do that. Testing numerical methods for ODE. We should include our header file with constants here. That was main CC. That was main page. So we should define the parameters of our problem. So suppose we have defined the constant A, so 0.0, it's the left end of our segment. Then we define B, suppose it's the right end of our segment. Actually, that's maybe not convenient because we have this A and B. Okay, let's define it like, for example, X L and X right. We should define the A as I don't remember. In our examples, we took it like 3 and 2, right? So here A equals to 3 and define B equals to 2. Okay. So actually we defined our problem. We defined our problem. We should include the necessary files for input and for output information. H and then include mathematical functions. Okay, so all the preliminary steps have been done, and now we can move forward the implementation of our numerical method. So what should we have? First of all, we need our computational grid, right? Also, we need to have a constant which will define the number of the segments of segmentation of our computational domain. So define n equals to, for example, 11. So now n is the number of nodes. Here I usually have the number of nodes. So this is the left hand and the right hand, and so the parameters of our problem. Okay, we are going to work with memory and so on, so just static arrays. So xn is the array of our nodes, and at each node we should know compute the numerical solution. So un is the numerical solution. The numerical solution. We want to compare our numerical solution with the exact one, right? U exact is the exact solution, and we want to see the plot for error. So error of n is the errors. Then we want to check different numerical methods. For that, we should also introduce a number of constants for that. So we use the enum or enum. It's the user-defined type of data. So we defined enum as for Euler, for central difference numerical scheme, and for unstable. So they are for this scheme, and for this one. We also unstable. We also want to check different norms. Then num L1, L2, Linf. So usually constants, capital letters are used for constants. So they are for one norm, two norm, and infinity norm. Okay. So then we should specify which numerical scheme we are going to use. So in scheme, for example, we will start with explicit Euler scheme. It's just Euler, and in norm we would like to use, for example, L1 norm. Okay. We should start with the building of our computational grid. So first of all, we should compute the coordinates of our nodes. Computational grid. So actually, this is just C, but I also use some convenient features from C++. I from 0 less than n was plus. Yeah, we should define our H step. So our H step is xr minus xl over n minus 1, right? It's our time step. No, not the time step, just step. We have just one variable. It can be interpreted as time or space, it doesn't matter. So if you know h, now we can say that xi equals to x left plus I multiple times I times h, and yeah, that's it. So it's our computational grid. So one of the most important things that you should be able to work with debugger when you work, right? For example, here in Visual Studio, it's very, very convenient. So we can start our debug, check that h is reasonable, so we can see that so everything is correct. So we can see y, xy, and so on. So Then we should define our initial condition, right? So u0 is b. So u0 is b. I mean that we're solving this equation, and so u0 is b. Okay, then we should have our main cycle, right? In which we will compute our computational result for we start with 1 because we know u0, right? So we need to start with the first inner point of our computational domain. So u0 is the boundary value, or actually initial value, and so we should start with 1. We also need to compare our numerical solution with the exact one. That is why we should also define u exact at 0. It's also b. It's also b. Then we want to check different numerical schemes. So we use the following construction: switch scheme. And then we can use case and different constant options. Euler, then case central, then case unstable, yeah, and case default and default. Yeah. That's it. Okay, let's implement the numerical scheme for I mean Euler scheme, this one. So this one. It means that u I equals to 1 minus a times h u I minus 1, right? Yeah, we compute, then break. And here we need to compute the exact solution. The exact solution of our problem is, do you remember? So it's b times x, because of we use the math h, we have access to different mathematical functions, minus a times x, y, right? Yeah. And we also want to compute immediately error at each point, just to plot it. So it's just u I minus u x y. Okay. Fix small errors. Misprints, in fact. Okay, so we computed the Euler scheme. Now we should compute the. Yes, we should also initialize. Maybe not so important. Now we should compute the norm. So this is type of norm, and then we should define the norm of error. We should initialize it as 0, and now we should have another switch. Norm. We have three different options. L1. Actually, in the same manner, you can define not only one norm or two norm, you can define p norm. So just for any arbitrary p, but in practice, so 1 and 2, so they are widely commonly used. Case L infinity break default. For L1, we should norm plus equals to h times r I. Right? So Ri is absolute value of difference between the current numerical solution and exact solution times h. That is why we just implemented this norm for error, because we need to compute the norm of error. Yeah, okay, that's it. And after that, we need to check our result. We want to see the numerical solution, the exact solution, the error, and we need to see the norm of error. And usually we can also have some print message to check that everything goes well. Yeah, for example here. Yeah. It's just the message that the process of numerical solution goes. After that, we need to write our results. For example, we did for write format write text. Usually, so you should always check that so your file really was opened. And finish. Okay. Yeah. So we want to open file. After everything, we will close it. And here we should write the necessary information. We need write what? We need to write x, numerical solution, exact solution, and error, right? So we should do it inside in a cycle. So I less than 8, I plus plus. I'd like to show you, because I want to show you that all these complex theoretical concepts, they are very interconnected with real practice. So you really need to know all these theoretics if you want to get accurate results, and if you want to understand what do they mean, what they mean. Xi u I u x I and r I, and just slash. Okay. Let's check. Let's try to run it. Okay, so we took just 11 nodes, so the simulation should be very rough, but you can say we have some error. So this is our Euler date. Oh, we can see we have error here because we did not define it at. Oops. Okay, so this is these are the coordinates of our nodes. This is the numerical solution. This is the exact solution. This is an arrow. So you can see that you can see my mouse, right? So we can see that initially our numerical solution is the same as exact solution. The error is 0. Then we have some error. It becomes bigger and bigger. Actually, you can remember from our previous lecture that it's like this hill-like shape because of some the structure of this main error term, and then it becomes smaller and smaller. Okay, you can use any software for analyzing your results. I use software called TechPlot. It's a very powerful tool for scientific visualization. If you have 2D, 3D simulations and you need complex, visualization as the software is, and so on. But now it's very simple, but it's still very convenient to use it. Below this Euler. Yeah. So this is the numerical solution. We can rename it. Let's say that it's new numerical, and this is the exact solution, and this is an error, and we can plot both here and error on the right axis. And so I use this software to write all these illustrations. So it's very convenient. You can use different styles and so on and so forth. So it's very convenient for writing papers, right? So we can use dots here, whatever you like. So the red line is the numerical solution and the green line is the exact one, and so you have already seen these pictures. So now everything is ready for numerical experiments. So we can use different norms, grids, and different numerical schemes. We will do it after the break. let's continue. So we simulated we numerically computed our problem with the use of explicit Euler scheme. Well, for example, we can take the more detailed grid. So it's just 11 nodes. Let's take 21 nodes. So you can see the errors becomes smaller. It's very convenient to just replace it here. You can see obviously the error becomes smaller and the correspondence becomes greater, so better and better. Okay. Anyway, this is the first order scheme. We will check it later. Let's implement central difference scheme. And I can remind you that the idea was that we want to get more accurate result. We have this central scheme. Then we should go here and write that U. But here I can also remind you that we have some problem. We need to define somehow a U1 grid. So here we have two options. Two options for U1. So if E equals to 1, then U I. Consider the first option. U1 equals to U0. Else means that for I equals to 2 and so on. Then we should use this formula. Un minus 1 minus 2 A H Un. Un minus 1, it means U I minus 2. And because we can be here only when I equals to 2. That is why I minus 2 is defined, so everything is okay. Minus H A U I minus 1. Okay. And here we want to use not Euler but central. And let's keep the result for the Euler equation and write it in the file called central. Let's check. So we can see something is wrong. Or maybe the computational grid is is not accurate, or maybe we made some mistake. Let's check it more accurately. Yes, I missed H. Yeah. So now it works, and we have some errors, but actually you can see that errors here are big. So one more time, we tried to get more accurate result because we took, second order scheme. Yeah. So several conclusions, right? So first of all, the behavior of this curve, the red one, so it's qualitatively different in comparison with Euler equation. So Euler equation, for the Euler equation, the curve was always, I don't know, up or lower than the exact one. Yeah, for the Euler equation, the curve was always lower than the exact one, monotonically, and it monotonically decreased, and it mimics the exact solution. So our exact solution monotonically decreases, and also our numerical solution also monotonically decreases, And I also would like to remind you that we should keep in mind that we do not solve some abstract problem. We solve some physical problem, and so all the results should be considered like, so it's like some model equation for some real physical problem. And if some physical quantity should, decrease, that's very bad if you have some, this oscillation curve. And it means that, the accuracy is not it's not enough. And actually, even here, there are some other properties of your numerical method that you should take into account, and maybe you can take less accurate form of a numerical method but which provide you more physically relevant results in comparison to more accurate numerical method. But anyway, still the result looks so. Actually, the result is correct. So there are no mistakes here. But it's not monotonic, and the error becomes bigger and bigger. And so maybe the computational mesh is too root. Let's try to use, for example, this one. Oh, not debugging. Not debugging. Start without debugging. You can see that results now they're better, and maybe if we still take more accurate computational grid, even here the error will be smaller and smaller. So actually here the result is maybe not so bad, but still, so it looks like this non-monotonic curve. But in fact, the thing is that we used this option for U1. It was the first option, but theoretically this scheme should be big O of H. Let's check what will happen if we will take U1 in this form. And one more time, we proved theoretically. So these results we obtained from theory. That is why one more time, all these theories are very important. A times H. We just slightly improved and made more accurate prediction to U1. Okay? So that's a miracle, right? We have the much more accurate result, but still, it's still not monotonic. You can see 1 point lower the exact solution, 1 point upper than the exact solution. So yes, this effect is very small, but because we took the here, it's visible here. So it's not monotonic. Maybe it's still not appropriate for you. For example, if you want to physically relevant solution, maybe these oscillations are not okay for you. And anyway, you should keep it in mind. But so indeed, the central difference scheme can provide you more accurate solution in comparison with so here we also have some oscillations. What about Euler scheme? So how will it look like for this computational grid? Let's now central scheme, Euler scheme. Can compare them. Why not? You can add. So for example, this is the numerical central. Add Euler. So just very convenient. So you can use any other software for drawing. So the black curve is for Euler equation. actually, that's not so obvious which one is better or not. So we can check the formal accuracy, and we'll see that apparently the central difference scheme indeed is the second order scheme, and the Euler scheme is the first one. But anyway, if your computational mesh is small enough, the distinctions, the difference between the here. But for initial time instant, for sure, you can see that central difference scheme is much more accurate. So you can see that the black curve is the Euler scheme, and the red curve is central difference scheme. And for initial time instance, so for early time steps, for sure, central difference is much more accurate if you compute the U1 in an appropriate way. Okay. What about unstable scheme? Let's check it. The third option. The third option is unstable numerical scheme. Here again we have the problem of the choice for U1, because here is the mix between the first order scheme and the second order scheme. And so we still need the same option for U1. Let the U1 be the same as here, and then minus 2. Plus 3 plus minus 2 plus 3 plus AH. So this one. You can check at home that this numerical scheme is the first order indeed. So if you think that you understand what's going on, you can just check that the consistency of this numerical scheme, and check that the accuracy order of this numerical scheme should be the first one. But the problem is that the scheme is not stable. And then unstable. Oh, we didn't change here. Yeah. So you can see a very typical result. You can see the infinitely big errors, but everything starts with some reasonable small values. But with each next step, you have bigger and bigger errors, and just after the 10th one, you have absolutely unreasonable values. But at the same time, it's not just an error. You don't have not a number. You have just constantly growing errors. So this is a typical behavior of numerical of instability. So yeah, so the numerical solution is unstable, and that is why you're not able to use this numerical scheme for your simulations. And you can take smaller mesh or I mean cell size or bigger, doesn't matter. So it will not work. So the last question is now we want to check the accuracy of our numerical method. We computed the L1 norm, right? Let's also print it. So we want to use this option. So we want to check that in this space, logarithm h, logarithm error, indeed the slope of this curve equals to accuracy order. For that, let's print the necessary information. And see, log function is natural logarithm. That is why we can just take this one, log of h and log of I don't know, and that's it. So suppose we want to check it for Euler equation. L1, and let's take rough computational measure. Just 11 nodes, so very, very rough. So Euler. So you can see this logarithm of h and this logarithm of norm. Let's accuracy check. Yes, I want to check it. Then we take this value and this value. Then we want to compute using 21 more nodes. And we have this one. And this one. And for example, 41. So you can see the difference between two neighboring values is about 0.73. And here is also about 0.73. Now we can plot this graph. So actually this is a straight line with inclination angle 1. So we can check it. So it's shifted, so it starts not from just 0, 0. It is shifted. You can remember that here we have this logarithm c. That is why for different norms and for different age it will move, but actually the inclination angle will be just 1. Wow. We can check. Let's check this for central scheme. It's interesting to see what will happen for central difference scheme with the correct, not correct, but most accurate choice of U1. So yeah, this choice is correct, and we should choose central scheme. Central. And actually, you can see it's very fast. If you know what to do, it takes you just I don't know several tens of minutes. So usually so that is why I'm surprised when I give such a task for students. Sometimes they're not able to do that at all. and 41. So this is for Euler scheme. This is for central scheme. So I think if we check, we will see that here. So actually that's the difference. So the scheme with the first accuracy order and then the scheme with the second accuracy order. So that is why it's very important to realize all these theoretical concepts. And I think that I explained to you the importance of all these theoretical concepts that we discussed previously. Okay, so you can actually implement, and if you're interested, you can implement different norms, L2, L infinity, and check that the specific values of these norms, so they will be different, but the result should be the same. So for example, here it should be like norm plus h times power I2, and after that you should take square root. So if norm equals to L2, then norm is square of norm. That's it. L2 and maximum value. So if I is bigger than norm, norm should equals to Ri. Right, because Ri is just the absolute value of error in specific node, and then you should just compute the maximal one. So these are three norms, and you can also check that you can take any of them unstable schemes, and that's it.